In 1977, humanity launched a spacecraft that has been flying non-stop at over 38,000 miles per hour for almost 50 years. It's called Voyager 1. And today, it still hasn't left the solar system. Not even close. If our fastest, farthest traveling machine can't escape our own cosmic backyard in half a century, what makes anyone think humans ever will? To understand why leaving the solar system is so hard, we first need to understand how big it actually is. If we shrank the sun down to the size of a basketball, Earth would be a peppercorn, about 30 meters away. Pluto would be over a mile away. And the edge of the solar system, the Oort cloud, a shell of icy debris, would be roughly the distance from New York to Los Angeles, several times over. Voyager 1, our farthest human-made object, is currently about 15 billion miles from Earth. It still needs roughly 300 more years just to reach the inner edge of the Oort cloud, and about 30,000 years to fully pass through it. Only then would it be considered outside the solar system. Let's say we wanted to reach the nearest star system, Alpha Centauri. It's about 4.24 light-years away. That sounds close. Until you realize light itself takes over 4 years to get there, and light is the fastest thing in the universe. Our fastest spacecraft ever, the Parker Solar Probe, moves at around 430,000 miles per hour. Impressive. But at that speed, reaching Alpha Centauri would still take about 6,600 years. To make the trip in a human lifetime, we'd need to travel at a meaningful fraction of the speed of light. And that's where physics starts fighting back. Accelerating even a small spacecraft to 10% of light speed would require an almost unthinkable amount of energy. More energy than humanity currently produces in decades just for propulsion, not counting fuel to slow back down. Rockets work by throwing mass backward to push themselves forward. The faster you want to go, the more fuel you need. But that fuel itself has mass, which means you need even more fuel to carry the fuel. This is called the tyranny of the rocket equation, and it scales exponentially, not linearly. To reach even a modest fraction of light speed with a chemical or even nuclear rocket, the fuel-to-payload ratio becomes so extreme that the math essentially breaks down. Some calculations suggest a starship would need more fuel mass than exists in the observable solar system just to reach a nearby star and stop. Even if we solved propulsion, our own biology becomes the next wall. Outside Earth's magnetic field, astronauts are exposed to intense cosmic radiation that damages DNA and increases cancer risk. A multi-year or multi-generational voyage would expose crews to radiation doses far beyond anything considered safe today. Then there's zero gravity. Long-duration spaceflight causes muscle atrophy, bone density loss, vision problems, and immune system changes. NASA's studies on astronauts who spent a year in orbit found significant physical effects. And that's with the ability to return to Earth. A journey lasting decades or generations with no way back is an entirely different level of biological challenge. And then there's the psychological side. Isolation, confinement, and the sheer weight of knowing you'll live your whole life, and maybe your children's whole lives, inside a metal tube and never see Earth again. One proposed solution is the generation ship, a massive vessel where multiple generations live, reproduce, and eventually the great-great-grandchildren of the original crew arrive at the destination. It sounds elegant on paper, but it introduces enormous risks. You'd need a fully closed-loop ecosystem, capable of producing food, recycling air and water, and remaining stable for centuries without any outside resupply. A single major system failure, disease outbreak, social collapse, or genetic bottleneck could doom the entire mission with no rescue possible. Some researchers have also raised a strange but real concern. Over hundreds of years in an artificial environment, isolated from Earth, culture, values, and even the ship's original goals, could drift or be lost entirely. Here's the twist. The solar system itself is enormous and largely unexplored. There's more usable material in the asteroid belt alone than humanity has ever mined on Earth. The moons of Jupiter and Saturn may hold subsurface oceans with real potential for life or resources. Mars, the Moon, and orbital habitats could support millions of people long before interstellar travel is remotely feasible. In other words, it may take us centuries just to fully settle our own solar system. And by the time we're capable of building interstellar ships, we may not even need to leave. We'll have an entire system's worth of room to grow into. So will humanity ever leave the solar system? Based on physics, biology, and engineering as we understand them today, the honest answer is almost certainly not. Not in any time frame that resembles a human lifetime, or maybe even a human civilization's lifetime. But that doesn't mean the story ends here. It just means our next frontier isn't a different star. It's the rest of our own backyard. A backyard we've barely even begun to explore.